Hi, my name is Tiagi, and this is my AP Calculus BC 2025 full exam review. So how this is going to work is each day I'm going to post a video going through one of the units for the AP Calculus BC exam. Today we'll be going over Unit 1, tomorrow will be Unit 2, and so on. Be sure to subscribe so you get notified when I post the next unit, which will be tomorrow. And before I start, I'll go a little about me. My name is Tiagi. I'm a junior from New Jersey. And why am I doing this? I'm doing this because I'm actually taking the AP Calculus BC exam this year too, and I thought to myself, what better way to, learn the material and revise it than to teach it? And I thought about that. Why teach it to nobody when I can teach it to all of you guys? So that's why I'm doing this. And yeah, there is no script. It's just me reading my notes, so it might be a little unstructured, but it should be helpful. So without further ado, let's get started. Alright, so Unit 1, limits. So the definition of a limit is the value a function approaches as it approaches a certain number. So let's look at this graphically. If we have a function, let's say like this, call it x squared, the limit at a certain point, call it at c, is the value the function approaches as you go from the left side, from the right side, sorry, and as left side. It approaches a certain value as you get to values closer to c. You're not getting at c, you're using values closer and closer to c. And as you get closer to c, you approach a certain number, L. That's the limit at c. How do we notate this? We notate this as limit as x approaches c, so the arrow means approaches c of, in this case we're using x squared, so we can do x squared, we could also call it f of x, and we say equals L. Because again, as we approach c from the left side and the right side, we approach the singular constant value L. So the more formal definition of a limit is if f of x becomes arbitrarily close to a single number L, so it's becoming arbitrarily close to a single number L, as x approaches c from either side, we say that f of x has a limit L as x approaches c. So graphically, an easy way to find a limit is just to see what it approaches. Now, in what cases would a limit not exist? Well, a limit does not exist if the left-hand side, the left-hand limit, so limit as x approaches c from the left hand, we use a negative sign to dictate the left hand, does not equal the limit as x approaches c from the right side, which we use a positive sign for that. When will this happen? Well, let's imagine we have the function f of x equals absolute value of x over x. So in this case, the function would look like this. We'd have a jump like that. And so if we take the limit at x equals here, then we're going to see that there is no limit because the left-hand side limit does not equal the limit from the right-hand side. Therefore, there is no limit there. Next, the limit doesn't exist if it's unbounded. So if we have a function, for example, f of x equals 1 over x squared, we'll get a function that looks like this, right? And so while there are limits everywhere else at the point c equals 0, there is no limit. Because even though they both approach infinity from the left side and the right side, which satisfies this, it's not a constant number. It has to be L, a constant number. And so in this case, we have no limit. But sometimes we like to dictate it as this. We like to say that limit as x approaches 0 of f of x equals infinity. Now, while this says there's a relationship, this just shows us the end behavior. It's not actually the limit. It doesn't exist, the limit in this case. But we can dictate the end behavior by using this statement at c equals 0. And finally, the last case is if there's oscillating behavior. I've never seen this on an exam, having oscillating behavior for a limit, but for example, if we had a limit as x approaches 0 of sine of 1 over x, you see what will happen as x goes closer to 0, sine is going to fluctuate even more rapidly until it's fluctuating at like an infinite amount of times in that small space. And so because the value is fluctuating from -1 to 1 really rapidly, it's not approaching a singular value at x equals 0. Therefore, because it's not approaching a value, there is no limit there. And one important thing to realize is when you have a limit, the limit can still exist even if there's a hole in that function. Okay, so let's say we have a c there. That's what we want to evaluate the limit for. There still is a limit even though there's no value at c. Because again, the limit tells us the value of functions approaching as we approach it from the left side and the right side. It's not telling us the value at a point, it's telling us the value as you approach it from either side. Okay, so we just reviewed how to find out a limit graphically if it's indeterminate, doesn't exist, DNE, or if it does exist. But now, how do you find it analytically? So analytically, you have a couple methods to figure out what the limit is, what the limit is of a function. So the first thing you can do is direct substitution. This works if the function has no hole at where you're evaluating. So for example, you could do limit as x approaches 2 of x squared. In this case, if we just plug in 2, we get 2 squared equals 4, and that's the limit. And the reason this works is because there's no hole in the function. X squared is continuous on all intervals -infinity to infinity. So this is the first thing you should always do when you're evaluating limit analytically, check if direct substitution works. But what if it doesn't work? Well, there's some other rules we can try using. So we can also try dividing out the function by factoring. So an example in this case is, let's say we have to take the limit as x approaches 1 of x squared minus 1, or sorry, x cubed minus 1 over x minus 1. So in this case, if we plug in 1, we get 0 over 0, which is indeterminate. When I say indeterminate, what I mean is that we don't know if the limit exists or if it doesn't exist, because it's giving us a value that doesn't tell us much. So what we have to find out another way to evaluate it. So in this case, we can try factoring. So if we factor out the top of this expression, we get limit as x approaches 1 of x minus 1 times x squared plus x plus 1. So here, the x minus 1's cancel out, and we're left with a value of 3. And the last thing we can do for evaluating a limit is we can do rationalization. This works if we have a square root in the limit. So let's say that we have this limit as x approaches 0 of square root of x plus 1 minus 1 over x. In this case, we plug it in, we'll get 0 over 0, which means we have to find another way to evaluate the limit, because we don't know if it doesn't exist, because it's indeterminate. So in this case, we can multiply the top by the square root of x plus 1 minus 1, or sorry, plus 1, the conjugate, right? If we multiply the conjugate, we'll remove the square root, and we will multiply the bottom by the same thing from the top. And the reason why is because we want to multiply by only 1, and so this is 1 because it's a over a. If we do that, we're going to get limit as x approaches 0 of x plus 1 minus 1, because again, square root of x plus 1 times square root of x plus 1 minus 1, and times x square root of x plus 1 plus 1. So you'll see here that the 1 minus 1's, that becomes 0, and we're left with x in the top and x in the bottom. So because we have that, we can just cancel them out because they're just factors. So x cancels out, and we're left with 1 over square root x plus 1 plus 1. Now we can plug in 0, and we get the value to 1/2. So that's rationalization. And those are the main techniques you'll use for evaluating limits analytically. There also are some limit properties. So let's say we have two functions or two limits. So we say limit as x approaches c of f of x equals L, and limit as x approaches c of g of x equals k. The properties are, if we add the two together, if we add limit as x approaches c of f of x plus or minus g of x, all in the same limit function, and the value is L plus or minus k. Similarly for division, if we put inside the limit sign f of x times g of x, the value is L times k. Same thing for division, f of x over g of x, L divided by k. Also, we have some scalar properties too. So if we have the limit x is c of, let's say, k times f of x, we're allowed to just move the k out of the limit sign and just call it k times L, because limit as x approaches c of f of x is L. There's also the composite rule. So if we have limit as x approaches c of f of g of x, then this becomes, we can just move the limit sign inside the function. So it becomes f of limit x as approaches c of g of x. And those are all the rules you need to know. There's also a power rule, but again, same idea. We can just move the power. We can move the power outside the limit. Okay, next we'll go with trig limits. So there's two limits you guys need to memorize for the exam. These are special trig limits. The first one is that limit as x approaches 0 of sine of x over x, where x is anything. It could be 2 of x over 2x. The important thing is that x and x are the same, equals 1. And the limit as x approaches 0 of 1 minus cosine of x over x equals 0. Those are the two trig limits you need to know for the AP Calculus BC exam, and these are actually very useful, and we'll go through an example right now. So let's say we're trying to find a limit of, let's say, limit as x approaches 0 of tangent of x over x. So if we plug in 0 and 0, we're going to get 0 over 0, which is determinant. So we can try using one of these rules. So let's say that we do limit as x approaches 0 of sine of x over x times 1 over cosine of x. And so what I just did here is I just took tangent of x, which is sine of x, over cosine of x, and I rearranged it to put sine of x over x, because now it's one of our rules, and I put 1 over cosine of x. So if we remember one of the rules of limits, what we can do now is we can just say that limit of x approaches 0 of sine of x over x times limit as x approaches 0 of 1 over cosine of x. And again, this is just our product rule for limits. So this becomes 1 based on our rule. And then if we plug in here, we get 1 too, because 1 over cosine of 0 is 1. And so the final answer is 1. So these limits are very useful, and you'll see them pop up quite a bit on the exam. Next, continuity. So continuity states that a function is continuous at a point if 1, the function f of c exists at the point c, right? If the limit as x approaches c of f of x exists, and the two f of c and limit are equal to each other. If all 3 points are true, then the limit is continuous at that point. And so what does continuity mean? Continuity means if we have a function, right, and we just put our finger on it, then we don't have to list it up at any point to draw the function. It's continuous. There's no holes, there's no jumps, and there's nothing that'll disrupt continuity. Speaking of disrupting continuity, when could this continuity be broken? So the function's continuous if we can't lift our finger off the page when drawing it. So if we think about it, the times where we will lift our finger off is if there's a hole in the function. So let's say we have a function like this, and there's a hole. That's discontinuous there. These are discontinuities. That's a hole. It's also discontinuous if there's a hole and there's a point right there. That's a gap discontinuity. These are removable discontinuities, right? Because we can fix them by defining the function at this point. But there's also non-removable discontinuities. So non-removable discontinuities are functions like this. So let's say we have a jump discontinuity. It's non-removable because we can't just add a point to fix it. There's also infinite discontinuities. It's discontinuous, even though it's continuing, it's discontinuity here because we have to lift our finger off the page. It's not in one line. You have to take your hand off the page to draw. And finally, there's also oscillating. I've never really seen oscillating discontinuities, but if you have a function that's oscillating really, really rapidly at some point, like sine over 1 over x at 0, it's discontinuous because its limit doesn't exist. And so why are these rules important and why do they work? They work because, think about it, if f of c doesn't exist, then we get a hole, right? If the limit doesn't exist, then we have a jump, or we have a infinite discontinuity, or an oscillating one, basically a non-removable discontinuity. And if these two aren't equal, then we get something like this, and we have this. Basically, we have a hole and we have a point, but they're not equal, so it's not continuous. You also have continuity on a closed interval, so it's a function is continuous on a closed interval a to b if the function is continuous on the open interval a to b. For these, you can just say, oh, it's a polynomial function, therefore it's continuous on the open interval, or it's a blah blah function, therefore it's continuous. And it's also continuous if the limit, as x approaches for a from the positive side of f of x equals f of a, and vice versa, limit as x approaches b from the negative side of f of x equals f of b. So basically, these last 2 points that you're checking if it's continuous at a and b. And if it's continuous at a and b, and on the open interval, it has to be continuous on the closed interval, ab. So when would you ever use this closed interval continuity? You would use it for IVT. So for IVT, intermediate value theorem, how you set it up is you first say it's continuous on AB, and you use the rules I just defined before. It's continuous on the open interval, it's continuous at the points, and then continuous on AB. And you define that a of f of a, which is the first point, is equal to some value n. F of b is also equal to some value called m. And because of this, these three things, since f of x is continuous on AB and k, to say that there is some k, there must be some k in between f of a and f of b such that f of c equals k and c is in the closed interval AB. So this might seem kind of complicated, but really it's not saying too much. It's just saying that if we have a function like this continuous from a to b, and the function has f of a here, f of b here, that's the values, then we're saying that there has to be some k. If we choose a k in between, let's say k here, f of b, and f of a, so it's in between, then it's guaranteeing us there has to be some c, some value for c such that f of c equals k. And this kind of makes intuitive sense, right? If you have a function going from here to here, and it's continuous, meaning there's no holes, then you have to have some kind of line that goes through the k that we want. So there has to be some c. No matter where you go, you can go underneath, but you have to go up at some point to reach b. And therefore, you have to have some value of k such that this is true, if it's continuous. If it's not continuous, you could have a hole here, right? And then the value wouldn't hold. Okay, now the last thing for today is infinite limits. So infinite limits are limits that we take for n behavior. They dictate n behavior. So infinite limit is something like limit as x approaches infinity, plus or minus infinity, there's negative infinity, positive infinity, of some function. And these limits, while they don't exist, they tell us the n behavior of a function. So these are sometimes tested on the exam. They just test to see if you can tell what's happening as a function goes on forever. So in this case, to evaluate these, you can first, if you have a function like this, it's a of x to the n over b of x to the m, right? And you have some more terms, polynomial terms like that. And these x to the n, b, x to the m, these are the highest terms in the top and the highest terms in the bottom. Then you have some rules. So if n is greater than m, like that, then the limit is 0. If n equals m, the limit is a over b. And if n is greater than m, the limit is infinity. And why is this true? Think about it. If we have the highest term at the top is, let's say, x of n, x of m, and if m is greater than n, that means the bottom is going way faster than the top. And since it's growing way faster, it's going to approach 0. Similarly, if they're equal, then we're saying that because they're growing at the same rate, because they're equal, then a over b should be what it approaches because they're growing at the same rate and to the same value. Finally, if n is greater than m, since n is growing much faster than m, it should be approaching 0 because, infinity, because the top is going much faster than the bottom. There are some properties with infinite limits. We have the property that if you have some limit, let's call this limit equals L, right? Or equals infinity. And you have limit as x approaches, you have g of x. Yeah, if you have that, and you have the limit as x approaches infinity of g of x equals some value L. The same properties we had before of adding, subtracting still hold, so adding them would be infinity. Multiplying it, if L is negative, it would be negative infinity. If it's positive, it would be positive infinity. If we do L divided by infinity, we get, 0. Infinity divided by L, we get infinity, etc. And last thing that's important to know is the acronym Tom likes pizza every Friday night. This stands for trig, logarithmic, polynomial, exponential, factorial, and n to the n. Basically, what this tells us is how fast the function is growing. So it starts from the slowest to the fastest. These are helpful. This acronym is helpful when we're trying to evaluate n behavior. So let's say we have the function limit, or the question limit as x approaches infinity of, let's say, x to the 1000 over x factorial. So in this case, it's kind of tricky to find out where it's going, because if we look at the top is growing pretty fast. It's x to the 1000, but the bottom is also growing pretty fast too. So we use this acronym. So we see that polynomial, which is the top, is less than factorial. And because of this, because the bottom is going faster than the top, based on our acronym, then it has to approach 0 as it goes to infinity. And the crazy thing is, no matter what value we choose for the top, we can have 1 billion, we can have whatever, we can have as many zeros as we want. This will always be true, because the way the factorial grows is so much more faster in the way the polynomial grows. And yeah, so that's how we use the acronym. And that was Unit 1 at the AP Calculus BC exam. Thank you guys all for watching. If you have any questions or if I made any mistakes, please let me know. This is my first time making this style of teaching video. And yeah, that's it. Make sure to subscribe to be here for tomorrow's video. And once again, thank you guys all for watching. Bye.